Hello, this is a lecture series for Chemical Engineering Thermodynamics 1, and at this point we are at lecture 2b. This is part 3 of lecture 2b. From the previous two parts, we talk about the calculation of enthalpy change mostly, and in the last part, the second part, we talk about the enthalpy change with respect to the change of phase in the system. Okay, and we also discussed about the calculation of enthalpy change comparing between or using indirect paths. In some cases it might be more convenient, or sometimes we have only data for some other condition rather than what the system really take. Okay, for this part we will discuss the calculation of the change of enthalpy when the reaction is taking place within the system. The first example would be the reaction between calcium carbide, water, in order to get calcium hydroxide and acetylene. Okay, and if we consider the reaction to be two states, the reactant can be considered as initial state for the process, and then after the process is done, the process is really the reaction. If the process is done, what we have or what we obtain is basically a product at the final state of the system. Okay, so we can say that this one is initial state and then the product is the final state. Mathematically, we said that the change in enthalpy is basically the enthalpy of the final state subtracted by enthalpy of initial state. For this particular example, the final state contains two components or two compounds, and initial state also contains two compounds. So we have to take enthalpy of each compound combined at each state. Okay, if let's say assume that somehow we can obtain the number, and the number here is 125.4 kilojoule per mole. We can state that at this given temperature of 25 degrees Celsius and given pressure of 1 bar, I say that it is 1 bar because the circle here is an indicator of the standard enthalpy change. The enthalpy change here is equal to minus 125.4. It means that the final state has lower enthalpy than the initial state. It also means that if you start with the state with high enthalpy, undergoes reaction, and the final state has lower enthalpy, according to the conservation of energy, the extra amount of energy must be released, and it cannot go within the system. It will be released out of the system, and therefore the system here is called exothermic. It releases energy out of the system. And since the pressure here, this circle indicates that the pressure of the initial state and the final state are the same, and therefore we can say that the pressure, the process itself is a constant pressure process. Under constant pressure condition, the change in enthalpy would be the same, or is exactly the same as heat. We can call delta H under a constant pressure process to be heat, right? Therefore, that's why we call this one as heat of reaction. Okay, so even though this is what we feel coming out of the reaction, but initially heat of reaction was defined based on enthalpy change. Now, if you consider this sentence, I said that the products are formed at same temperature and pressure as reactant. And I said that the process can be considered as constant pressure process. The question that you might ask, can I say that this process is isothermal? Because the initial state and final state share the same temperature. Can we say that it is isothermal as well? The answer is yes, you can. Then you have to be very careful about this. If it is isothermal, does it mean that the internal energy does not change? Now the answer is definitely no. Okay? From the very beginning, we said that internal energy has three factors affecting internal energy: temperature, phase, and chemical composition. In this case, even though temperature are the same for initial and final state, but chemical composition is changing. Okay, so this is an obvious indicator that inside the system the internal energy will be changed. Once the internal energy is changed, enthalpy, which is also a function of internal energy, H equal to U plus PV, H will be changed as well. The third question would be, here I said kilojoule per mole. Mole of what? Is it the mole of the first compound? Now, sometimes it would be very confusing for someone, especially when the stoichiometry number here are not 1. All right. So please keep in mind that the term kilojoule per mole here, the number of mole right there, supposed to correspond to the compound which has the stoichiometry coefficient of 1. So per mole of calcium carbide, or you can say per mole of calcium hydroxide, or per mole of acetylene. Okay? So you have to be clear. So as long as the reaction is written like this, it means that once the reaction takes place fully, the energy would be changed, or the enthalpy would be changed by this much. And under constant pressure condition, that change in enthalpy would equal to amount of heat released. Now let's say that the starting point is 25 degrees Celsius. The final state is 25 degrees Celsius. By doing so, the heat must be released by this much. But think about this one. For exothermic reaction, if energy released by the reaction cannot be transferred out of the system fast enough, what would happen? Let's say you have 125.4 kilojoule per mole to be released out of the system, but the system cannot be cooled fast enough. It would end up that the product obtained here will be heated up by the energy that cannot be released out of the system. Okay, so if the cooling is not sufficient, then there will be a chance that the product will not have the same temperature as the reactant. And this is very common, especially for exothermic reaction like combustion. When you burn a piece of paper, normally the temperature will be raised because we cannot release energy from the fire fast enough. Okay, so in that case, if let's say we want to calculate delta H at 25 degrees Celsius, but the actual process makes the product to have temperature as high as 300 degrees Celsius. Now we want to calculate the delta H for this process, the red line. How can we do that? This is the red line represent what I call here direct path. It is the actual path taking place within the system. Alright? The point is, the number 125.4 at 25 degrees Celsius and 1 bar is the standard value that can be obtained from many textbooks that can be calculated. The way we calculate it will be explained at the end of this lecture. Okay, so let's say we can get this number, but the number that we obtain is usually presented at 25 degrees Celsius, but this time we want at different temperature. Not only is not 25 here, it's also different than initial state. Now what can we do? What should we do to get the answer? Alright, if you recall last 2 lectures, I try to explain that sometimes when the data is available in different conditions than the direct path that we have to take, it is better to go indirect path. Okay, so what kind of indirect path can we draw here? So it is obvious that the red line is direct path. Now the indirect path should go in the way that we have information. So the black line here, we have information, so we can go from the reactant to the product at 25 degrees first, simply because we have data over here, and then we can heat up the product up to 300 degrees Celsius. Heating up like this is just the change in temperature, so therefore the enthalpy associated with change in temperature can be calculated from integration of Cp dt from 25 degrees Celsius to 300 degrees Celsius. Note that here that Cp that I wrote here in pink is a Cp of calcium hydroxide. Okay. However, on the product side, we have 2 compounds. We also have acetylene, and therefore you need to heat up acetylene to 300 degrees Celsius as well. The change in enthalpy here would be integral of Cp dt, and this Cp would be Cp of acetylene. So I call this one delta H1, this is delta H2, and combination of change in enthalpy for each small step in the indirect path should equal to delta H for the direct path. We can get this relationship. What we want here for the red path would equal to combination of all steps in the indirect path. So the black line, pink line, and the purple line combine. Okay? Now, some of you might wonder, can we do this instead? Instead of going from the reactant toward the product at low temperature and then raise temperature of the product, can I raise temperature of the reactant to 300 degrees Celsius first and then convert from reactant to product at high temperature? Can we still get the answer? Theoretically, any indirect path that you choose, it should give you the same answer as the direct path. But sometimes it might not be that simple. I will explain to you right now. If you choose yellow, green, and brown path, okay, in that case, delta H would equal to H3, delta H3, delta H4, and delta H5 combined. The problem would be like this. There are 2 problems actually. First, delta H5 here is essentially heat of reaction at 300 degrees Celsius, which normally is not available. That's the first trouble that we are looking at. The second one is not so obvious. The second one is the green line. If you look at the green line, basically we are converting water at 25 degrees Celsius to water at 300 degrees Celsius. But here it is stated that water must be liquid. Okay, can you see the problem now? Water cannot exist as liquid at 300 degrees Celsius and 1 bar. So this green line is impossible. Okay, so even though theoretically you can choose any path that you like, but practically some paths might not be feasible. So you have to choose the indirect path carefully. Alright, so this is a lesson. The second part of this lecture considers the combustion reaction. If we consider combustion, it is basically oxidation, and normally it is exothermic. The energy change or enthalpy change associated with that is called heat of combustion. The reactant for the combustion simply is called fuel. Okay, so you have methane here as a fuel, oxidized with oxygen. For combustion, for complete combustion, on the right hand side the product would be carbon dioxide and water, and the enthalpy change associated with this reaction is called heat of combustion, or delta HC, and this one is taking place at pressure 1 bar according to this standard indicator. Okay, so now it is said that under 1 bar the heat would be released by this much. I said heat because under the constant pressure condition, change of enthalpy would equal to heat. Alright, there's another reaction that we can write. Same methane react in the same manner, but this one, the product, one of the product water here, stay as vapor. Okay, in this case you see that the heat of combustion or heat of reaction here would be a little bit smaller in magnitude comparing to this equation, simply because if you look at water, let's say normally we are more familiar with combustion producing water vapor. Alright, so this reaction is more common. Let's say it's easier to understand. If we have to convert this water vapor into liquid, vapor has higher energy than liquid. In order to condense them into liquid, you need to release energy out of the vapor so that vapor can be converted to lower energy state. That amount of energy released from condensation will be added to this energy, and therefore the reaction, the upper reaction here, should release more energy. Okay, so if you subtract these two numbers, the difference is basically energy required for the vaporization of water. The first reaction on top, then this number, the enthalpy change associated with this reaction is called higher heating value, or HHV. If you work with mechanical engineer, they will use this number. They will use this abbreviation HHV. At the bottom here, the number is called LHV, or lower heating value. The difference between these two is that for actual application, for the calculation of amount of energy released from combustion, we would use LHV, because conventionally after combustion water would stay as vapor, because after combustion the temperature is high enough to get water evaporate into vapor. HHV will be used as a limit. This tells you the highest energy that this fuel can produce. Alright, if we consider several kinds of hydrocarbon, you see that this is the heat of combustion, and different hydrocarbons produces different amount of heat combustion. In other words, when you try to burn these fuel, it will generate different amount of energy or different amount of heat. One compound in particular has very high heat of combustion. This one, octane. This is the same word in octane number of the gasoline. So in the past we will try to have octane in the gasoline as much as we can. Right now we try to make a number to tell the energy released from gasoline to be equivalent to the number of octane. Okay. Another compound that has very high heat of combustion is sugar. Here is sucrose. Sucrose has also very high heat of combustion. The question is, why don't we use sucrose in our car instead of octane or instead of gasoline? The answer is basically the sucrose is harder to process because it is solid. Okay, unlike gasoline, which is liquid, it would be easier to supply into our engine. But human being or any living organism usually relies on sugar because this is very efficient. Very small amount can produce a lot of energy. So that's why our body requires sugar. The measurement of heat of combustion can be done in a device called calorimeter. It's basically a vessel, insulated vessel. You put a fuel inside there and ignite and measure amount of heat. But there's a limitation associated with using calorimeter in some cases. Let me show you an example. If I want to get heat of combustion from the burning of coal, let's say carbon, okay, charcoal or any kind of coal, pure carbon, and I would like to get the energy change or enthalpy change associated with this equation. So on the right hand side, instead of carbon dioxide, I like to get carbon monoxide. So this is incomplete combustion. Okay, if I want to learn the heat of combustion or heat of reaction for this particular reaction, what should I do? Can I put some charcoal together with oxygen and measure the change in temperature so that I can calculate heat from the calorimeter? The answer would be sometimes it would be very hard, especially if the reaction is at low temperature. Just imagine a piece of charcoal together with oxygen in air at room temperature. No matter how much you try to ignite the charcoal, it may not get burned because the temperature is very low and rate of reaction at low temperature is normally low. Okay, so sometimes measurement should be done at higher temperature than what we want. Let's say we want the temperature at 25 degrees Celsius, but in the actual measurement you need to heat it up to higher temperature. The second problem is that sometimes conversion might not be completed. Let's say you put 100 grams of charcoal in there. After you try to burn it, not all 100 grams might get burned. You may have some part of charcoal left. So amount of energy measured might not be associated with the total mass of charcoal you put in there, unless you have to measure how much you have charcoal left, which is sometimes very difficult. The third one, this is the most important one. Sometimes there are other products together, and it is very hard to control the reaction to be this reaction. Only this reaction to be is very hard to control to be like this. For instance, if you try to burn charcoal together with oxygen, in addition to carbon monoxide, you will get carbon dioxide as well. So that would be very hard to control the burning to produce only carbon monoxide. Okay? So what should we do if we experience such problems? Now it is time to use indirect path. Okay? So directly it is hard to directly measure the heat. So we can somehow draw indirect path and do the calculation to obtain the number. How can we get the indirect path? The heat of reaction of this one is the direct path that we want. I can add half mole of oxygen to the left hand side and to the right hand side so that the equation remains balanced. Okay? I also know that if you put the ratio of oxygen and carbon to be 1:1, it is easier to intentionally convert charcoal to carbon dioxide. It is easier to try to control the burning to be complete combustion. Okay? So in order to completely convert charcoal into carbon dioxide, that can be experimentally done. If the change in enthalpy here is called H1, then I can draw another reaction, the dissociation of carbon dioxide to carbon monoxide and oxygen to be H2, to be delta H2. Of course, you might argue that this reaction from carbon dioxide to carbon monoxide does not really take place, because carbon dioxide is more stable than carbon monoxide. But on the other hand, we can always convert carbon monoxide and oxygen to complete the combustion into carbon dioxide. So reverse reaction can be experimentally done. Alright? So if we take this blue path to be our indirect path, then the value of the delta H that we want can be obtained from the combination of delta H1 and delta H2. Okay, the left hand side is direct path, the right hand side is combination of indirect steps. For the first step, the complete combustion of carbon with oxygen to produce carbon monoxide can be obtained here, and the heat of reaction associated with it is basically heat of reaction 1. For the second steps, the oxidation of carbon monoxide into carbon dioxide can also be experimentally done, and this heat of reaction 2 can be obtained. If you take the first equation to be equation 1, this is the second equation, the reverse of the second equation is what we use for delta H2. Okay, so let me call this one the equation -2. When you reverse from product to reactant and reactant to product, the heat associated with it should have the sign change. So this one should have the sign to be negative delta R2. Then we can ignore this equation 2 and take equation 1 and equation -2 to combine. So 1 subtracted by, or 1 added by -2, it is equivalent to 1 subtracted by 2. So you can cancel the same compound from the reactant side and the product side, like carbon dioxide here, this and that can be cancelled out, leaving only carbon. Oxygen here, 1 mole would cancel with half mole of oxygen, leaving only half mole on the left hand side. At the end, we will get this equation, which is the same as what we want to measure for heat of reaction of our direct path. For the heat of reaction is basically combination of delta HR1 and minus delta HR2. Okay, By manipulating this small reaction and manipulating the delta H associated with it, this is what we call using the Hess law. Okay, manipulation of these small steps, adding, subtracting this H of reaction, is called using the Hess law. What is Hess law? By its statement, Hess law is basically this: if the equation can be obtained from the operation of small steps reaction, then the heat of reaction associated with it would be performed or would be operated under the same manner. That is called Hess law. Okay? Another way to do it, I can explain using this equation. Pentane reacts with oxygen to get carbon dioxide and water. So this is basically combustion of pentane. If I want to find delta H associated with this reaction, what should I do? If I highlight each component by using different color, the green one can be obtained. Let's say we can obtain the energy change or enthalpy change associated with the dissociation of pentane to carbon and hydrogen. For oxygen, it remains the same, but I put delta H2 for the sake of completeness. For carbon dioxide, I can say that it is a product from the combination between carbon and oxygen. In other words, you can burn carbon or charcoal to get carbon dioxide, just like our previous example. And then for water, we can combine hydrogen and oxygen to get water. The enthalpy change associated with each step is a highlight there. Okay? Then we can put the left hand side into the right hand side and call this one reaction 2. So if you use indirect path, you start from this state. This is our initial state, and this is final state. Okay, instead of going directly through this path, we can go down here and go to the right hand side and up there. This is our indirect path. By doing so, delta H for the direct path is equal to combination of all steps in the indirect path. So I take delta H1, 2, 3, and 4 combined together with delta HR2. Okay, this is the way we use indirect path. Now you should realize that this delta HR2 is essentially 0, simply because this side of the reaction and the right hand side of the reaction are essentially the same. You can see 5 carbon here, also 5 carbon there, 6 hydrogen on both sides, and 8 oxygen here. The blue one and the purple one combined are equal. Okay, so essentially this line does not take place. The reaction does not take place. Delta HR2 here is basically 0. We can also use Hess law in here. So if we are going to use Hess law, we have to split this whole reaction into small steps. Okay, so if I use the same steps here, like the green one, red one, blue one, and purple one, okay, so manipulating these 4 steps together, basically we combine them together. It might look the same as what we did for indirect path, but conceptually this is what we call Hess law. So when we try to combine them, pentane on the left hand side remains on the left hand side. The oxygen here, the oxygen red one here, these two cancel out. So we have 8 moles of oxygen on the left hand side, right? Carbon would cancel out, hydrogen would cancel out, leaving only carbon dioxide and water, just like this equation. So basically you take these 4 steps and add them directly. So the delta H for the whole equation should equal to summation of delta H of all steps. Just the same as what we did for indirect path. Alright. Now, we also know that this delta H2 is 0 because oxygen here and oxygen there remains unchanged. So there's no energy change associated with it. Delta H2 is 0. You can cross it out. Now, if I reverse the green reaction, I take the product of the green reaction to be written as a reactant and take pentane to be a product. Okay? By reversing the reaction, the heat or the enthalpy change associated with it should be reversed in sign. So this is minus delta H1. If I take delta H3 and 4, which belongs to the product of this reaction, I write it first, and then I write the product, or I write the reactant to be down here. Okay, so I can rearrange this equation to be delta H3 plus delta H4 subtracted by minus delta H1. That's still equal. Then, if you notice this blue reactions, okay, there are 5 here, there, and there. I can take this stoichiometry ratio number 5 taking out. By doing so, I can apply the same concept to this equation. I can take number 6 out. If you go back, this is 6, 3, 6. If I take 6 out of this equation, the second term here would become 6 multiplied by half. Okay? In that case, for the first reaction, let me define the whole delta H here to be called delta HF of pentane. Notice that the reaction here, pentane is the only compound on the right hand side of this reaction. So the change in enthalpy of this reaction is called delta HF of pentane. F here stands for formation. It is change of enthalpy of the reaction that forms pentane. Okay? For the second one, if you consider only the black letters, you can see that this is formation reaction, or the reaction that forms carbon dioxide, and the heat associated with it can be said to be 5 times of the heat of formation of carbon dioxide. Similarly, here is a formation of water. So this is what we call heat of formation of water. Then you can multiply it by 6 to get the same number as delta H4. Okay? All of these are called heat of formation basically because all steps, each single equation generates only one compound. Okay, so it forms this particular compound. Another unique feature of heat of formation, or the formation reaction, is that the reactant on the left hand side are supposed to be compound or element with only one single element. For instance, carbon here is an element, right? It's a single element. Hydrogen here is not element, it is a compound, but this compound contains only one element. So every reactant on the left hand side of the formation reaction must have a single element. Alright? The reason that we try to limit the formation reaction to have single element reactant is that when you put it like this, single elements can cancel out easily. So I can replace delta H3 by 5 times of heat of formation of carbon dioxide, and so on. For the reactant here, this is the minus delta H1 is basically heat of formation of pentane. So in summary, when you use heat of formation, basically you take heat of formation of the product multiplied by nu here, which is stoichiometry coefficient. Okay, you should notice that 5 and 6 here corresponds to 5 and 6 of the stoichiometry coefficient in the reaction. Okay, take the multiplication of stoichiometry coefficient with respect and with multiply with the heat of formation for all products combined, and then subtracted by those of reactant. Okay, the result would be enthalpy change for the whole reaction. So just like these examples, when we try to use this equation, you consider product first and trying to find heat of formation associated with each product. You take heat of formation of carbon dioxide multiplied by 5, heat of formation of water multiplied by 6, add them up, and then subtracted by heat of formation of pentane multiplied by 1, and heat of formation of oxygen multiplied by 8. The thing is, whenever your compound has only one single element like oxygen here, the heat of formation is essentially 0. Okay? And data for heat of formation for different compounds or various kinds of compounds are normally available in the thermodynamics handbook. However, conventionally, heat of formation data are available only at 25 degrees Celsius and 1 bar. So it is sometimes called standard heat of formation at 25 degrees Celsius. This is the conventional data that are available. For at other temperature and other pressure are extremely rare. Okay, especially at other pressure, the data are extremely rare. So if you have to calculate reaction at other temperature than 25 degrees Celsius, then you need to find the heat of reaction from heat of formation at 25 degrees Celsius first, and then use indirect path to change the temperature of product or reactant, just like what I show you from the very first example in this video clip. Okay, so once again, the formation reaction, the characteristic of formation reaction is basically 1 mole of substance formed as a product. So on the right hand side, there must be only 1 mole of substance. On the left hand side, reactants are elements or compounds with single elements in the reference state. What does it mean, the reference state? Just like this. Carbon can exist in many forms: diamond, graphite, charcoal. Different forms should give different amount of heat. So in order to pick them as the reference state of heat of formation, the state must be specified. So you need to look up for proper state. Okay, normally it would be graphite for carbon. For examples, this is the formation reaction. One compound on the right, all compounds on the left are consisted of only one element. This is not the formation reaction, simply because on the right hand side the number here is 2, not 1. So this is not considered as formation reaction. This one, even though the number here is 1, this is also not the formation reaction, because the reactant on the left hand side are not single element. Okay, calcium oxide contains 2 elements. So As a summary for this lecture, in order to calculate heat of reaction, we can use indirect path. This is also very useful when the temperature of reactant and products are not the same, or temperature of the reaction are not the same as the data that are available. We can use Hess law to combine small steps together to get the reaction that we want. And then we can also use standard heat of formation. These two, especially Hess law, sometimes it is inconvenient simply because heat of reaction for each step that is used in Hess law must be known. Okay, so if each small steps of the reaction that you use is not standard reaction or is not formation reaction, then using Hess law requires knowing the heat of reaction. So that sometimes would be hard to get. So instead, people would prefer to use heat of formation. It is more standardized and is more preferred because the data are already available. The key is that the heat of reaction, if you use standard heat of formation, the reaction is limited to 25 degrees Celsius. So if you want to calculate the reaction at any other temperature, then you need to combine it with the calculation using indirect path. Okay? So all the content described in this lecture 2B are in chapter 4 of the textbook written by Professor Smith that we use in this class. The textbook is Introduction to Chemical Engineering Thermodynamics by Professor Smith. Okay? Next lecture, for the next video clip, I'm going to go back to chapter 3 to describe what we call equation of state. So thank you for watching.